Hello and welcome back to Steam with Steve. Today we're going to keep going with Boolean logic. So we're going to unpackage some of these things that you need to know for your exam. So Boolean logic, basically there's another branch of algebra that can be attached to Boolean, which then allows you to sort of use that these set of rules that you can apply, and it makes your ability to shrink the circuits down a lot faster. So if you've got the Boolean constants, you've got 0 and 1. You've got the variables, so these can only take in an input of 0 or 1. You then have functions, which is the and, or, not. And then there's some theorems and laws, which we're going to unpackage, which will then hopefully help. So first of all, we've got a thing called the identity law. So we need to think, what is 6 times 1? Well, that just gave us 6. 23 times 1 gave us 6. That huge number times 1 gave us that huge number. So when we multiply 1 by 1, that is what we call the identity. So what we input in, we get exactly the same output. The same works with adding. So if you add on 0, it works out exactly the same. So the identity law, if we look at this, if we had and, if we have 0 and 0, that gave you 0, 0 and 1 gave you 0, 1 and 0 gave you 0, 1 and 1 gave you 1. Then we can also talk about variables, so we can make this a bit more generic. So if we have a and 0, that will always give a 0, because it doesn't matter what the state of a is. If we have 0 and a, it gives you a 0. If we have a and 1, that will always turn the system on, so that will give you a. 1 and a will give you a. And then if you have a and a, it will give you a. And then if you have a and not a, it will give you 0. Similarly with or, so if you have 0 or 0, these are exactly the same as before. But now if we have variables down the bottom, if you have a or 0, it would just equal a. So see how that simplifies it down? If you have 0 or a, gives you a or 1 gives you 1, 1 or a would activate the system, and then a and a would give you a and not a would give you 1, because that would be all the different situations. So not 0 becomes 1, not 1 becomes 1, and then not a becomes the flip. These are all the identities of every single possible combination that can occur. And the following laws can be followed through this website here. I'll put the link down below, but that gives you some pretty neat things. You then have the communication law, which basically means it doesn't matter the order. So 5 plus 4 is exactly the same as 4 plus 5. However, if you subtract, it's a little bit different. So when we're dealing with and or, it doesn't really matter the order that you do. So if you have the and operator, a and b is equal to b and a. Same with the or operation, a or b is the same as b or a. The distribution law, bit of an algebra thing here. So if you have brackets and you put something out the front, you can go through and expand and times everything inside of it. So 4 bracket x plus 1 is equal to 4x plus 4. So when we expand the brackets, we just go through each thing. When we do the same with and or in our Boolean algebra, it's exactly the same. So if we had a and b or c, and a out the front, you just have to go through an and a with each of the elements. Similarly, if you have a or b and then a or c, it actually works out the logic of the truth table to be the same as a or b and c. So that's one of those distribution laws that can help. The association law, 7 times 4 times 3, is the same as the brackets there. So there's an association, the brackets don't matter. So if we have a times b times c, it's the same as a times b times c with the brackets. And similar when we do or. The absorption law, so basically this forces something not to exist and absorbs it. So if you have a plus a or b, it's just equal to a. So you don't need to have that other part. And that sort of makes sense. Remember when we did things in parallel, it stops the circuit from occurring. You have a and a or b, it also just equals a. The last one's De Morgan's law, which is kind of cool. So a and b, all the not of it, is equal to not a and not b. And similarly as well, a and b, all the not of it, is equal to not a or not b. There are some special cases, so this is pretty cool. So this is where we get to use some of the rules. So if you have a or a and b, if you have them next to each other, it's the same as times. You can rip an a out the front and have a bracket 1 plus b. And then we remember, if you have 1 plus something, it just becomes 1, because then it works, and then this becomes a. So a is equivalent to a plus a, or a and b. which is kind of cool. And that's one of the rules. The next one then is A and not A or B. Basically, you can throw an A and a B in the middle between that. And then what happens then, because that is equal to 1, you can have a common term of the B and take that out the front. So that becomes A or B. Then, because A or not A, that becomes 1. So then that comes down here. So then this becomes the same as A or B. So instead of having three operations with an or, not, and an and, that becomes just an or, like so. So there's a couple of these laws. You don't need to know them off by heart, but that definitely does help and can improve your performance in HSC exams. So implement the following Boolean operation. You can then convert this into a truth table. So there's A, or, not B, and C. So not the B, and then the C. And then if you want to implement that function, sorry, if we go back, that's not quite right. Sorry, it should be not C. That's shifted across. So not C happens first, then it's B and C. B and not C, and then see how that joins in with that. Then if we want to implement that one, so not A, B, or C, not D, and then the not of it all looks something like this. So I flipped the A, so it's not A, flipped the D, so it's not D, and then join the not D with the C, then join the not A with the B, and then or those two together, but then the not of it all to get that response. It then is possible to convert a circuit diagram into a Boolean expression. So if you're given something like this, you should be able to convert that back by unpackaging it. So this is the same as not A. This is the same as not A or B, but the not of it all. This is the same as B, C. And then this is the not of all those merged together. This is a really handy trick for changing truth tables into logic circuits. Now, the important thing is to look for the key cases. So in this case here, there's only 3. There's this one, and then the one second from the bottom. So what you should see here is not A and not B and C is true. And, or A and not B and C is true, or A and B and not C is true. So if you go through the steps, you find all the cases where they're true, which is those 3 that we just found. Step 2 then is joining all the cases with an or statement. And then step 3 is looking for rules to try and simplify those down. So that's what that circuit would look like there, which is kind of cool. So can you simplify these with different rules? Absolutely. So instead of having this really complex one here, that simplifies down to BC or C. So there's a quick little video that's really handy to go through. Here's the styles of questions that you're going to get. So there's the Boolean algebra with all the different rules. Consider this algorithm, write a Boolean representation of the circuit. So that's the same as A and B, not B, plus AB, plus not A and B. Then this one here, a logic circuit has inputs A and B and one output Z. So if Z is 1, the output of A is 0. If Z is also 1 and the inputs A and B are not the same, otherwise Z is equal to 0. Draw a circuit. So you may draw a truth table. I'd draw the truth table out first, so then you can get your head around it, but then that's what would happen. So it's the same as a NOT gate with A and B, and then Z is the output at the end. Using AND, or you could have a NOT going into an OR with an XOR gate for A and B to get the same thing, which is pretty cool. Then consider this truth table here. Draw a circuit with the logical equivalence to the circuit below, which uses the fewest amount of gates. Support your answer with relevant truth table. That was pretty much what I did there. So this is straight out of the necessary exam, and what you should see is the NOT of XOR as well. So it helps if you're able to simplify the circuits down and then get exactly the same answer. Students are asked to design the circuit of a particular problem. 2 solutions were submitted. One was this, the second solution was this. Show the 2 solutions are logically the same. So you could do it with just a simple truth table, or you could use the Boolean logic that we've done before. Personally, I would just use the truth table because it's a lot easier. But you could also play around with the Boolean logic and then show and prove that it is the same. Consider the following logic circuit, the relationship between the outputs and inputs of the circuit is shown in the table below. So A is 1, A is 0, and C is 1, A is 1, B is 0, A and C is both 1, and then the output is that. So design a circuit that satisfies these conditions using no more than 2 logic gates. So this one's a little bit tricky and I love it. Basically, you've got some answers that you could use. It was A and C with an OR gate coming out to give us C. And then you could have gone through the Boolean logic here. So you've got A plus A naught and C plus A B naught and then AC. You can rearrange that to have A B naught plus A naught C plus AC, and then that groups down to that. And then this is where it's really cool. This can then simplify down to just AC if you use the rules that we just covered before, which is then the same as that. Or you just use a truth table and then punch it out and then see where all the patterns are and then build the circuit. So for the following circuit, it shows this output Z is always 1 whenever input A is 1 regardless of other inputs. So there's the truth table again. So drawing the truth table out, and then you can show the connections behind how that looks. A logic circuit requires 3 inputs and 1 output. The output of the circuit is 1 and at least 2 of the inputs are 1. Otherwise, the output is 0. Draw the circuit that meets these conditions, and then there's the little circuit for you. So you have A, B, C coming in, and then it joins and matches the truthness. Consider the following circuit here. Design a simplified circuit which performs the same functions. Justify design with using truth tables. There's the truth table, and then perform the functions, and then there it is as well. This one is pretty cool. So an art gallery is displaying a valuable painting. To protect the painting, the gallery installs a security system with 2 switches and an infrared sensor that can only detect movement within the painting's display area. The alarm will be triggered if only one switch is on or both switches are on and the sensors detect no movement. So you've got those sensors with that happening there. Complete the truth table to show the relationship between the input of the device's security system and then design a circuit. So that's what you should punch it out, which is pretty cool. That's a lot more complex question, but it's also a really cool question as well. So that's it from me. Hopefully that's given you some things to consider with your different circuits and how they work. The more you practice this, the better you get at it. And my advice is to play around with the NES's exams because they've got a whole more type of these questions. So if you haven't gotten those, what I would do is go back, pause the video, and then try and do those questions and then try and get your head in the game. That's it from me. If you did enjoy the video, give us a like and subscribe down below. And if you do have any questions, please put them in as it does help with that algorithm. So see you next time on STEAM with Steve. Adios.